Much has happened since Americans first landed on the moon. Since then, space has become a globally utilized resource. Our skies are now filled with satellites. People are living aboard the International Space Station, and scientists worldwide study our solar system with robotic missions. A new human space exploration enterprise is being launched that requires a focused strategy, a strategy that will enable us to explore new worlds, develop innovative technologies, and foster burgeoning industries, all while increasing our understanding of the Earth and our solar system. This new focus will allow us to work on objects in Earth's orbit, such as the International Space Station and satellites, while also exploring near-Earth objects, such as asteroids, the Moon, Mars, and Mars moons. But travel to these destinations won't be easy. It will require us to develop cutting-edge technologies to help us survive and thrive in these forbidding, faraway places. To help us understand and plan for this type of exploration, we first have to test systems and operational concepts on Earth and on the International Space Station. One very effective way to accomplish this is by using analogs, which is a representative environment that has similar features of the target mission's environment. This can include locations underwater, in the Arctic, on terrestrial impact craters, in the desert, on volcanic lava flows, and on the International Space Station. These extreme environments greatly enhance the ability to analyze architectural concepts in simulated conditions and enable experiments with long-range and long-duration expeditions. The NASA Extreme Environment Mission Operations Project, or NEEMO, utilizes the only underwater research facility in the world, the National Oceanic and Atmospheric Administration's Aquarius habitat. Working in partnership with NOAA, NASA uses the Aquarius habitat because it provides some of the best conditions for practicing space operations in a harsh environment. This unique setting has informed exploration operations in a simulated reduced gravity environment and demonstrated procedures with human and robotic collaborations. Testing in this extreme environment gives astronauts a broader knowledge and awareness of exploration risks, issues, and objectives associated with near-Earth asteroid missions. There have also been numerous discoveries made during NEEMO missions on human health, engineering, telemedicine, space operations, education, and public outreach that directly relate to spaceflight needs and that are being implemented with each mission. The Desert Research and Technology Studies Team, or Desert Rats, conducted their 13th annual field test exercise in August and September 2010. The Black Point lava flow and SP mountain areas in Arizona were the sites selected for the test because its terrain, geologic features, size, and dusty environment are similar to what would be encountered on other surfaces in space. The Desert Rats field test allows NASA to test high-fidelity prototype hardware under realistic communications scenarios in a representative environment. Over a 14-day period, the astronaut and geologist crew teams performed an over 300-kilometer science and exploration-driven traverse under different communications and operations scenarios, only getting out of the vehicle to perform simulated extravehicular activities, to collect geology samples, or to work in the habitat demonstration unit. The In-Situ Resource Utilization Demonstration Field Test took place in January and February 2010 at Mauna Kea, Hawaii. In the current exploration architecture, in-situ resource utilization has been identified as providing 1 to 2 metric tons of oxygen per year for astronauts during surface operations. The field demonstrations help to lower the architecture risk by their successful demonstration of end-to-end oxygen extraction, separation, and storage from the volcanic material. The in-situ terrain, rock distribution, soil materials, and permafrost at Mauna Kea provide good simulation for the polar regions of the Moon and Mars, and tests hardware and operations beyond ability of laboratory and available rock yards. These early demonstrations of in-situ resource utilization will provide lessons learned for subsequent hardware and mission concept development. In addition to the successful technical field test accomplished, this test, hosted by the University of Hawaii at Hilo's Pacific International Space Center for Exploration Systems, or PICES project, showed how successful collaboration between members from federal, state, and local governments, several other countries, multiple companies, and several universities can occur, serving as a good model for our future exploration missions. NASA and the Canadian Space Agency teamed up to sponsor the Pavilion Lake Research Project, conducted in British Columbia, Canada. This project is a multidisciplinary science and exploration mission whose objective is to explain the origin of freshwater microbialites that are growing on the bottom of the lake. NASA conducts analog missions at Pavilion Lake due to the critical science being performed and the extreme remote location, which provides a challenging setting to test and develop research and exploration methods for site surveys and science data collection. The way the submersible vehicles explore the lake's bottom surface is similar to how a robotic precursor mission would explore a near-Earth object, such as an asteroid. The process refinements for traverse planning and science data collection will help improve techniques for future space exploration missions and scientific research. The International Space Station provides a great platform to test out future exploration systems and operations. These tests include research to reduce the risk to humans during long-duration missions, autonomous operations needed for handling communication time delays, and exploration systems and capabilities. An example of these types of tests includes how humans and robots work together to overcome huge technical challenges. These human-robotic partnerships will be tested with the addition of Robonaut 2, or R2, to the International Space Station. The conditions in the space station will provide an ideal test bed for robots to work in close proximity to humans, while also working in a zero-gravity environment. The plan is to evolve the system with new software uploads and new subsystems like legs or mobility aids to eventually allow the R2 to work outdoors. This outdoor training will allow R2 handlers to better understand how the system will work in the vacuum of space, helping them prepare for future deep space missions. Not only do the analog field tests help NASA refine the strategy and technologies needed for human space exploration, but they engage the public by allowing them to participate, collaborate, and share in the excitement of exploration. The immersive environment created at the analog field sites allow citizen explorers and citizen scientists to work with robotic systems, astronauts, and scientists during analog exploration missions. These hands-on opportunities in science, technology, engineering, and mathematics, or STEM activities provided by the analog field tests inspire students and engage the public. NASA's plans to extend humankind's presence in space will require many technological advances and a greater understanding of how to use the systems to explore effectively. Analog tests on Earth and on the International Space Station will be key to achieving these goals.